Welcome to Mastering Solutions. The challenge with this problem is really just piecing together all the different equations to figure out how to weave your way through all this stuff. So it's important to have good organization with this to keep everything straight. So let's start off and write down what they give us. We know that the wavelength of this helium neon laser in air is 633 nanometers, which of course is times 10 to the negative 9 meters. We'll leave it like that though. And then we need to figure out what the wavelength in the liquid is. So let's put lambda air, and then we want the wavelength in L for the liquid. So that's what we're trying to solve for. And so ultimately what we're going to end up with is we're going to use the equation for index of refraction, and we're going to use wavelength in air over wavelength in the liquid, or whatever material you're talking about, and then we're going to find these two to solve for them. Now we already have the wavelength of air, so we have to figure out what the index of refraction is. And since we're here, let's rearrange this. So we have the wavelength in the liquid, which we're trying to solve for, of course, is equal to the lambda in air divided by the index of refraction. So now if we take a step backwards, how do we get the index of refraction? Well, we can use the equation of n is equal to the speed of light in a vacuum divided by the velocity in the liquid. But we don't know this, right? So we have to figure out this thing. So that's what I meant where we have to piece together these, where we have to go from this to this to this to figure out the answer. So they're really just making you do some gymnastics with all these equations, is it? So let's start off with, let's just figure out the velocity. We're going to use the velocity equation. So the velocity in a liquid is going to be equal to the distance over time. They gave us the distance, it's 30 centimeters. If we change that to meters, that's 0.3. So we have 0.3 meters, and they say it's 1.38 nanoseconds. So 1.38 times 10 to the negative 9 seconds. And that's how fast it was going through the liquid. So when we plug that in, we have 0.3 meters divided by 1.38 times 10 to the negative 9. So it was going, what is that in scientific notation? So we have 2.17 times 10 to the 8. So the speed of the liquid is 2.17, I'll go one more, 4 times 10 to the 8 meters per second. So now we can plug that in here to figure out the index of refraction. So now we have the index of refraction is equal to 3 times 10 to the 8 meters per second divided by this that we found over here, the 2.1, that was a bad 7, 1.74 times 10 to the 8 meters per second. That will give us the index of refraction. So we have 3 times 10 to the 8 divided by 2.174 times 10 to the 8. So that gives us 1.38. So n is equal to 1.38. And again, remember, there's no units for index of refraction, so that we know when we have meters per second divided by meters per second, that is correct. So now, finally, we can plug this in over here. They already gave us this. So we have 633 times 10 to the negative 9 meters divided by the n, which we found is 1.38. So we have 633 times 10 to the negative 9 for nanoseconds divided by 1.38. So that finally gives us the wavelength, which is 4.58 times 10 to the negative second. Usually wavelengths are listed in nanometers, at least for light. So let's move that over 1, 2. So we have 458.6. So let's go the lambda for The liquid is going to be 459 nanometers. And that is your answer.